FB. So these are the first order low pass and high pass frequency. Now let's go ahead and take a look at an example that how we can actually apply these filters to signals that we have. So if I have a signal, the input signal as in time domain as 5 cosine 2 pi t plus 5 cosine 200 pi t plus 5 cosine 2000 pi t, and then if I want to pass it through the so this is the input signal I have, and then assume I have a I have a filter like this, which I connect this signal to that filter, and that filter is has a R. And then it has a capacitance C, like that, and then we have this V out. So if we want to know if the R is 1000 divided by 2 pi and C is 10 microfarad, so that's O. If it's this one and it's this one, then what is going to be the output signal? So this is the input signal. This is our filter. So let me just draw our filter again. So this is the filter. And by looking at that, we know that it is the first order low pass filter because it's the RC, with the arrangement of the RC. So this is the filter. And then we want to see what's the output. So if it's the input, we want to see what's the output signal is going to be. So to do that, first of all, we have to see what is the cutoff frequency. So the first thing that I know the cutoff frequency here, for this one is FB is equal to 1 over 2 pi RC. So therefore, the cutoff frequency is going to be 1 over 2 pi times 1000 divided by 2 pi, and times the C, which is going to be 10 times 10 to the negative 6. So therefore, the cutoff frequency is going to come out as 100 hertz if we do the calculation. So now we know the cutoff frequency. So we know that this is a low pass. So by the arrangement, we can say this is a low pass filter. And this is the cutoff frequency. So basically, it tries to let all the frequencies that are smaller than 1 hertz pass through in the input signal. So whatever you see, our input signal has 3 parts. So it has 3 sections. So it's going to let all the part that is input signal has the frequency of less than 100 hertz pass through, and all the part that is all the signal that has a signal larger than 100 frequency, just reject them as much as possible or remove them um, as much as possible. So for the input signal, if I go ahead and say that this part is my, assume I have the V in, so I have 3 input signal. So my input signal is made of 3 separate inputs. So V in 1, this is going to be the V input 2, and this is going to be the V input 3. So I have assumed my signal is made of 3 signals. So my input signal made of 3 sinusoidal signals, and I want to see what happened to each of these input signals when they pass through this filter. So that's how we will do that. Remember, if we have the time, we have a signal in the time domain, we want to decompose it to the series of sinusoidal wave, and then we will pass through each sinusoidal wave to the filter to see what happened to that, and that at the end we add the result of every signal passed through the filter together to get the output signal. So let's start with the first one. So I know that the first input signal is 5 cosine 2 pi t. So again I know here that this is the omega t. So I can go ahead and say that, okay, for the first one, the omega is 2 pi. Um, so sorry, it's 20, not 2. Go ahead and fix this. So it's 20 pi t. So it's 20 pi t. So same here. So it's 20 pi t. So I know that, so it's going to be, so this omega t, so the omega is going to be 20 pi. And then we know that the omega is 2 pi f is 20 pi. So you know that the omega is 2 pi f. So just replace it there. And therefore the frequency of this very first signal would be 10 hertz. So it's the frequency of my first signal. And so I know my first signal was the frequency, and then I'm gonna just write it in the phasor domain. So V in 1. In a phasor domain, it has its magnitude, which is gonna be 5, and the angle that is gonna be 0, because it's plus 0 here, basically. So I repeat, so this is the first signal I have. Now I want to find the I want to see how this filter behave for that specific frequency. So I have to go ahead and say, okay, I know that is a low pass filter, and the HF for that low pass filter is 1/1 plus J over F over FB. So I know this. Therefore, now that I know that the F is 10 hertz, so I go ahead and say, okay, the end, my filter, so let me just write it here. So this is my, basically this is the HF. So that's my filter. So once see that filter at 10, if the frequency 10 hertz, is going to become 1 over 1 plus j, and the fp is 100 and the f is 10, so it's going to be 10 over 100. And if you go ahead and recalculate that, do the calculation in the polar format, what I'm going to get is going to be 0.995 with angle of negative 5.71. So this is my filter for that 10 hertz. So now I know that the V1, V out for the 1 is just simply, if I multiply this one, so is the H10 times V in for the 1. So remember that I just write it here. So the HF is the V out divided by V in. So for each of them, if I multiply the V in by the HF, I'm going to get the H out for that specific frequency. So I can also add for this here. So V in for that specific frequency. So I can use it the same here. So the V out for the first one is going to be the H1 for 10 hertz, which is going to be 0.995 with angle of negative 5.71, and then it's going to be multiplied by V1, which is 5 with the angle of 0, and then if you do the calculation, you will get 4.97975 with the angle of, so to multiply the magnitude and the subtract the angle, 71. And then if I go back and put it in the time format, so I can say V out 1 would be equal to this, the amplitude or the magnitude, 975 cosine the omega 1t. So the omega here is, and let me put it omega 1, so we know that, so it's the omega 1. So omega 1 is that, so the omega 1 is 2 pi 20 pi t, so it's going to be 20 pi t minus the angle, which is going to be 5.71. So this is the very first effect of our filter on the very first one, and we have to repeat this for the second one and the third one. So I'm going to write it for the second one and the third one as well. So if I go to the second one, I know that the input, the second one is cosine 200 pi t. So we know that this is going to be the omega 2t. So therefore we know that the omega 2 is going to be 200 pi, and the omega is 2 pi f, and here is the f2. So let me go back and also make that f1. So it's the f1. So it's going to be 2 pi f2 is equal to 200 pi, and therefore the f2 is going to be 100 hertz. So we know that it's going to be the f2, and then also we know that also I'm going to write this in a phasor mode. So the V in 2 is gonna be 5 with the angle of 0 again. Now I have to calculate the HF again. This, as I said, the HF is gonna be, you know, gonna be 1 over 1 plus J F over F cutoff frequency. So this time we want it for the 100 hertz. So the H for 100 hertz is going to be 1 over 1 plus J. And the FP is 100. This one is 100. So it's going to be 100 divided by 100. And therefore, if I rewrite it in form of the angular format, is in polar format, it's going to be 0.707 with the angle of negative 45. So, and then the V aught 2 is going to be the H100, so the F at F2, and the V in at 2. So the V aught 2 is equal to, so this is going to be the 707 with angle of negative 45, and that's the V or V in is going to be 5 with the angle of 0. So if you do the calculation, the V aught 2 is become 3.535 with angle of negative 45, or I can write it as the time domain. It's going to be 3535 cosine omega 2t, which is going to be 200 pi t, 200 pi t minus 45. So remember that when I'm using because here is the omega t is different, so this one is going to be, I'll just write it here. So this is the omega 2. So when you're going back and forth from phasor mode to the time domain, make sure that you use the correct omega t. And then the same here, we can do this thing for the last. So I'm going to draw the line here. So for the same for the last one. So V in the third input signal is going to be 5 cosine, as it was 2000 pi t, and again this is going to be the this is the omega 3, sorry, so omega 3t, and look at all this really has a phase of 0. So it's just because we wanted to compare them. So the omega 3 is 2000 pi, therefore 2 pi 3 is equals to 2000 2000 pi equal to 2000 pi, and therefore the F3 is 1000 hertz, and the V in 3, if I write it as it's going to be again 5 with angle of 0 if I write it as phasor. Again the same here, the HF the filter, we know it's a low pass, so it's going to be 1 plus J F over FB, and therefore the H, this time we have 1000. Let's see what's the effect of the filter if we pass this frequency through that. So we want to see how it's going to behave if it's the frequency is 1000. So it's going to be 1 plus 1000 divided by 100. The FB, the cutoff frequency is 100. And if you rewrite it as a polar format, it's going to be 0.0995 with angle of negative 84.29. So if I go ahead and says, okay, the V out for the third one is going to be the H1000, and the V in for the third signal. Therefore, V out for the third one is, this is 0.995 with angle of negative 84.29, and the signal is 5 with angle of 0. Therefore, V out for the third one, if you multiply the magnitude and subtract the angle, it's going to come out as 0.4975 with angle of, just subtract the angle, negative 84.29. And if I put it in the time domain, it's going to be the magnitude, which is going to be 0.4975 cosine omega 3t, which is going to be 2000 pi t, minus, if I can fit it here, minus 84.29. So let me write it down here. So I just rewrite the whole. So V out 3 for the time domain, it's going to be this magnitude, which is going to be 0.4975 cosine omega 3t, so it's going to be 2000 pi t minus plus that angle, which is negative, it's going to be negative 84. So negative 84.29. Let me delete this. And just remember that this part is, this is omega 3t. So make sure that also let me write it here as well. So it's the omega 1. So make sure when you're dealing with each of them, use the correct omega t. So remember that I convert everything to the phasor, I do the calculator, and I convert them back to the time domain. And the reason for that is that because we have the different omega for each of these three, we cannot add them or subtract them or do anything with them in the phasor mode. So remember, do not add them or subtract in the phase domain. Make sure that you convert them back to the time domain and then do any calculation you want to do. Now let me go ahead and so I'm gonna just write both of the signal again one more time. So the input signal, uh, the, the input signal in the time domain is, I'm gonna write it, so it's gonna be 5 cosine 20 pi t plus plus, and the second one was 5 cosine 200 pi t, and the third one was 5 cosine 2000 pi t. And then we have the output signal, which is equal to, if I want to write, so it's going to be 4.975 cosine 20 pi t minus 5.71. Then plus the second one was 3.535 cosine 200 pi t minus 45. And then the third one is 0.04975 with angle of, sorry, with 2000 pi t with the phase of negative 84.29. So if you compare these three together, so you will see that the 5 is changed to 4.95, and we know that the breaking or the cutoff frequency is 100. So this one, because it's much below the cutoff frequency, so it's 10. Its frequency is 10. Because it's much lower than cutoff frequency, you will see that its amplitude doesn't change much. So it just let that pass through, and it make a little bit change in the phase. So because this is a low pass filter, it's supposed to let the signal with low frequency just pass through without any change. So as you can see, the 5 doesn't change much, and here is 0. The phase is 0 and change to the 5. So both the magnitude and the phase of that signal doesn't change much. When we come to this one, which is it has a frequency equal to cutoff frequency, you will see that the 5 changed to 3.5, and the angle just 45 degrees changed. So this is where we are actually sitting on cutoff frequency. And here the frequency is 1000, so we have a very, very high frequency compared to cutoff frequency. And as I said, the low pass frequency is supposed to let the signal with low frequency pass through, and the signal with high frequency to be rejected. So if you can see, the 5 is almost becomes 1/10 here. So from the 5 it goes to the point, almost 0.5. And the angle changed the most, so it's 0, it goes to almost a negative 84 degrees. So as you can see, as it says, the low pass frequency, low pass filter, it let the signal with a low frequency to be passed through with a little change, and it tried to reject or remove the signal with the higher frequency as much as possible. Just one more time, say that we have to add them or subtract them here in the time domain. Make sure you are not doing the calculation in the phasor domain, because they have the different omega t, and because the omega t is different, we cannot add or subtract anything in the frequency domain. It should be done in the time domain. So we do the calculation in the frequency or phasor domain because it's easier, but then to add them or subtract them, we have to bring them back to the frequency domain.